Hello friends, today we are going to study Standard 10 Science and Technology Paper 1, Chapter 1 Kepler's Law. Planetary motion has been observed by various astronomers since ancient time. Before Galileo, that is before the discovery of telescope, the motion of the planets was observed by naked eyes. But by 16th century, lot of data was available regarding the motion and position of planets. Johannes Kepler studied these data. He noticed that motion of planet follows certain laws. He stated 3 laws describing planetary motion. So before beginning Kepler's law, first we will understand the concept of ellipse. Just have a look on the diagram. Now this is an ellipse. Ellipse means something like an oval shape which you usually see. Now students, in ellipse we have two focal points. I have written here F1 and F2 are the two focal points. We can also call it as foci. You can see here I have written 3 points over here. Okay, A, B and one more point C I have written. Now I just explain one concept. The sum of the distance of two focal points from every point on the curve is constant. F1 and F2 are the two focal points. That is F1 and F2 are the two focal points of the ellipse as shown. And if A, B and C are the 3 points on the ellipse, then it is given as AF1. You can see I have written here AF1. I have drawn over here AF1 plus AF2 will be equal to BF1 plus BF2 will be equal to CF1 plus CF2. If you draw many number of points, you can infinite number of points you can draw, and you can show you will get the same equation. Okay. So one more thing again I want to tell, in ellipse we have two focal points, or we can say we have two foci. Here I have shown F1 and F2. Now let's begin with the Kepler's law and understand the 3 Kepler's law in detail. Now let's begin Kepler's first law. So first we will see the statement of Kepler's first law. Kepler's first law states that the orbit of a planet is an ellipse with the sun at one of the foci. Now just have a look at this diagram. You can see this is the orbit of a planet which is in elliptical shape. It is not in circular shape, but it is in the elliptical shape. So orbit of a planet is an ellipse with sun at one foci. I have already taught you that the ellipse has two focus. So sun will be at one of the foci. So I will repeat the statement again. The orbit of a planet is an ellipse with sun at one foci. Now let's begin with Kepler's second law. We'll see the statement of Kepler's second law. The line joining the planet and the sun sweeps equal areas in equal interval of time. Now I'll explain this. Just have a look on this diagram. You can see a planet over here. Okay, so that position we will consider as position A. Okay, and after some time interval, you can consider, for instance, for example, you can consider time interval 10 minutes. After 10 minutes, the planet will travel to point B. Now while traveling from A to B within 10 minutes, it has traveled certain distance, and also you can see it has covered certain area. If you join the line, that is, now this is your sun over here, you can consider this point as S. If I join the line AS and BS, you can see some area has been covered by the point ASB. So this particular area it has covered. Now we will take some other point which is covering same interval of time. Now here I will take another point, consider point C. Imagine your planet is at point C. Again after 10 minutes it will travel certain distance and it will reach at point D. Means after 10 minutes it will reach point D. Here also you can see it has covered certain area. Okay, now this you will see that CSD, it has covered certain area. If I write this, that is, I will just write down here ASB will be equal to CSD. Okay, means the area covered by ASB will be equal to CSD. This was the Kepler's second law. I will repeat the law. The line joining the planet and the sun sweeps equal area in equal interval of time. The time period should be equal. When it covers the equal interval of time, it will cover the equal area. Now let's see the Kepler's third law. We'll see the statement first. The square of its period of revolution around the sun is directly proportional to the cube mean distance of a planet from sun. Now I'll just explain you this. Now consider the period of revolution. Period of revolution means time taken to complete the revolution. The period of revolution will consider as capital T. Is directly proportional to the cube mean of the distance. Mean distance. Mean distance means what? Now student, this is an ellipse. If it is a circular orbit, the distance will be same from all this from the center. But since it is an ellipse, the distance is different. So we have to take the mean distance. That mean distance I will consider it as r. Okay. Now what the law say? The square of its period of revolution. So it means T square, okay, square of the period of revolution is directly proportional. Directly proportional, I will put the proportionality sign, directly proportional to the cube of the mean distance. So, cube of the mean distance of planet from sun. Now, I will just remove the proportionality sign and I will get as T square is equals to, when we remove the proportionality sign, we have to put a constant value. We will consider constant value as K into r cube. Now what we will do, I will take this r cube on the other side and I will get T square upon r cube equals to k. This is Kepler's third law in the equation form. Again I will repeat Kepler's third law. Kepler's third law states that the square of its period of revolution around the sun is directly proportional to the cube mean distance of a planet from the sun. Now students, Kepler obtained these laws simply from the observations of the position and planets. It's like just was a normal observation he has done, but he had no explanation why planet obey this law. So we will see how the planet obey the law and all in the next lecture. That will be explained with the help of the Newton's theory of gravitation. Thank you.